Everything all right, baby? Everything all right? Okay. Come on in, everyone. Feel free to ask questions if you have any.
I have a question on a problem that's on the homework, but I can wait till after class if you want.
No, this is probably a good time.
Okay, I got stuck on a problem on chapter 25 homework.
Uh-huh.
Let's see, I'm gonna put it in the chat.
Okay. You can share the screen if you prefer. It's up to you though. I just made it where that's available to you.
Okay. So there's like 3 parts to it, and I got the first 2 parts just fine. The first part was estimate the electron drift velocity.
Right.
The second one was estimate the current density. But I got stuck on the third one.
Okay. This is a 0.70 millimeter diameter copper wire carries a current of 2.7 microamp. Estimate the electric field in the wire. Okay. There's another version of Ohm's law that's in your textbook. Let me see. I actually might even be able to pull it up in real time because I actually had to have the book open earlier. Let's see. Should be right here. More people coming in. So let me see what this shows. There's another version of Ohm's law. Instead of V equals IR, it's E equals J, yeah, I think it is J rho J. I'll double check on that. And if that's the case, then really you're just doing a simple multiplication. Oops, I didn't mean to do that. Okay. Let's see. Yeah, it's E equals rho J. Or if you want the conductivity, you could do J equals rho E. So what I mean by that is you were able to get J. So E equals rho J, where rho is the conductivity, the resistivity of the material. So you're dealing with copper here. So that's 1.68 times to the negative 8, if I remember correctly. And J is the current density, which is what you were just calculating, which all it is basically you take the whole current and you divide it by the power squared for the actual wire. So let me see if if what I calculate gives you the right value. I've explained it in words, and like I said, I'll double check with the value real quick. Let's see. So we had E equals rho J. 0.7 millimeters is the diameter, so 0.7 e to the -3 divided by 2 is the radius. So I'm going to square that and multiply it by pi. And that gives me a cross-sectional area of 3.84 times 10 to the -7th. And the current was 2.7 microamps. Oops, I understood the wrong exponent there. So 2.7 times 10 to the -6 microamps. So I got a current density of 7.01. And if you multiply that times 1.68 e to the -8, that should give you about 1.18 times 10 to the -7th. Volts per meter. That's the new unit, by the way. So I just posted that in the chat, but let me go ahead and share my screen as well now that I have it open. Let's see here. Working on it. Taking a little while, sorry about that. My document is kind of screwed up, so I'm trying to repair it at the last minute here. It should be done in a second. There we go. Still got quite a few students aren't here yet, even though it's time. Okay, let me go ahead and deal with this now. I'm getting a call from one of my faculty members. Oh, that's nice. So what we have is E is equal to rho times J. What we have is E equals rho times J. So now I can go ahead and share the screen, hopefully. Come on. It's taking forever. Oh, yeah, let's shoot here. Okay, so E equals rho J is the version of Ohm's law that I was hinting at. So you can say the electric field in the wire is 1.68 times 10 to the -8, because I think that's the resistivity of copper. By all means, correct me if I'm wrong. And then you multiply that by J, and J is 2.7 times 10 to the -6 amps divided by pi times 0.00, and I think it should have been 0.35 if I remember correctly, millimeters. So be 35 meters squared. And when I did that, I got the value that I suggested. Did anybody, did you try that number 1.18 times 10 to the negative seventh? Trying to remember who asked it. I thought it was Famada that asked it. Was that not Famada? Anybody?
That's right.
That's right. Okay.
Yeah.
That's
Good.
cool.
I see where I messed up.
Yeah, and I wouldn't necessarily say messed up. It's really odd that well, actually, were you able to find that equation E equals rho J in the book?
I'm sorry, I didn't look because I was.
Gotcha. That's not a problem. I was just curious because I went to look for it just now, and I knew I'd seen it somewhere, but I couldn't find it right then when I was looking. So I'm wondering if it's something that got dropped by accident when they went to the new edition. That occasionally, nope, that's not it either. Crap. That occasionally happens when you switch to a new edition, as you leave off things that you think are no longer important. But yeah, I don't see it listed on here, so that makes it kind of hard to do. Hopefully, if it's not in the book, they gave you a hint about it somewhere within one of the problems or within the problem the homework is set. But yeah, I don't see it. So hopefully, well, I know that helped because you at least got it right, so we're good on that one. Anybody else have any other questions? It is about time to start. I've got some very specific problems I'm planning on working for you because last time I gave you an intro to basically Kirchhoff's loop rule and Kirchhoff's junction rule. And Kirchhoff's loop rule and junction rule are rules that allow us tricks to solve circuits. So if you have a series of wires with connected to resistors and batteries, and they have various branches or nodes, as you might call it, and junctions, then it's not necessarily that trivial to actually figure out what the current is and what the voltage is at various locations. So Kirchhoff's laws, our Kirchhoff's rules, give us a way of doing that. So let me start off. I'm going to draw a simple circuit that we can use. This one's going to have a 12-volt battery. So I'll break this from the previous problem right here. I'm going to say it has a 12-volt battery, and it should be pretty simple in this particular case. So it's 12.0 volts. And then the wire runs into a 400 ohm resistor. And we don't even usually take the time to put ohms on these things. If it's kilo ohms, we put a K up there, but no omega. I'm just doing it this one particular time so you can sort of start getting used to it and that sort of thing. Similarly, we have one over here that drops off like this. This particular one is 500 ohms, and this particular one is 700 ohms. And then we come back to the actual battery, and it's like this. Okay. So one of the things I often do is not only do I try to solve circuits when there are times to solve them, but I also like to use a little bubble system where I poke a bubble up so I can check where the voltage is everywhere. And what I mean by that is if you're looking at a multimeter, if you're looking at a multimeter, which hopefully y'all have had some experience with that in class by now. Okay, your multimeter will have, I always forget which side, but I'm pretty confident this is the 2 ampere sides, this one being the 10 amp. Then there's a common, and then there's another circle that's V omega. Obviously you have a dial and a screen. Okay. If you imagine putting this on, let's say V with the dot with a line over it, then we know that we're set up on DC volts. Okay, if it was V with a sine wave over it, then it wouldn't be. But what you can do is you can take and connect this COM, and because you're allowed to call the zero of voltage zero anywhere, just like we could call the zero of potential energy zero anywhere, I could take this wire and attach it right here, and then take the red and attach it right there as well, and I'd read 0.00 volts. And the way I would indicate that with my bubble system is just 0.0 volts. And I might not even write the volt then. And then I could, again, I'm going to leave the black wire there the whole time. Now I'm going to put the wire from the V omega from this guy. So that's why I'll show it in blue. If I put it here, it will read 12.0 volts. Doing this, thinking about this is a really good thing for helping you figure out a circuit. So for instance, we generally assume that wires without resistors on it are very, very, very low resistance. Heck, you saw yesterday or last time you saw that we had a mile long length of cable that was on the order of a couple ohms. So you can see a 400 ohm resistor is a lot different from a wire. So in principle, even if the current is running right here, this should also be 12.0 volts. Now, in reality, you know, it's really probably 11.9999. But the main thing is, I want you to know that we're going to mostly treat it like that would be exactly 12. Not only that, you could say this point right here is 0.0 volts, as is this point right here, 0.0 volts. Okay, so using that kind of stuff can sometimes help you figure out what the voltage is across a particular element, meaning a resistor or something like that. What I'm going to do is recall that the formulas we derived last time were R equivalent series was R1 plus R2 plus ... and 1 over R equivalent parallel was equal to 1 over R1 plus 1 over R2 plus ... So when you're trying to analyze a circuit like this, and what I'm asking for, by the way, is what's the voltage across each of them and how much current is going through each of them. So my question is, in fact, V400, V500, V700, I400, I500, and I700, and let's say I battery, which is just equal to IB. I want to know what all this is. Okay. So let's start. When I go to attack a system like this, the first thing I do is I try to look for sort of the deepest, most embedded stuff. This one's not a big example, so it's kind of hard, but obviously, well, pretty much the only thing you start with at all right now is the two that are in parallel. So if I do that, if I take the two that are in parallel, what I end up getting is 1 over R. Actually, let me change it to red so I can say I'm working on a solution. So I can say 1 over 500 plus 1 over 700. Well, I can get a common denominator for that. I can make the common denominator be, say, 3,500, in which case I have to multiply the 1 over 500 by 7 over 7. And I have to multiply the 1 over 700 by 5 over 5 so that I get this, which is 12 over 3,500, which is 1 over R equivalent for the parallel. Okay, Now, if you do that, it's really not that bad. You're just going to be taking 3,500 and dividing it by 12, and it'll give you 291.7. So what that means is I can replace that part of the circuit. I'm going to draw just a part of it so we can fit it all in here. Now what I have is this guy, and then this guy. This is 291.7, which obviously is one extra sig fig, and this one's 400. Okay, so I just left the battery off so we can fit it. Now we have two in series, and that's a lot easier. So what we can do is we can say we now have the equivalent circuit, and it is in fact this, which is 691.7 ohms with that having one extra sig fig. And now we have a simple Ohm's law problem where we've got a 12 volt battery connected to a single resistance. So we know exactly how to solve this. And in fact, what we're going to get is I battery. So V equals IR tells us that I battery is equal to 12.0 volts divided by 691.7 ohms. So if I do 12 divided by 691.7, I get 0.17349. 0.01749. And the only reason why I wrote the 4 and the 9 specifically was because if I had rounded 5, that might tempt people to round a second time. So really all we should be doing here is those 12. So basically we have 4 sig figs going in. I treat it like it's 3 sig figs, but it's probably safer to just assume there's only 3 or 4 sig figs. So that's the current through the battery. But if you look, the current through the battery happens to also be the current through the 400 ohm resistor. So we can write that as well. Everybody see why that's the case? Anybody have any questions about why it wouldn't be or anything like that? Okay, so we've got that current. Now, what's neat about that is we can now use that if we actually do the resistance of the wire from the positive end of the 12 volt battery to the 400 ohms, we can figure out exactly what that 12.0 next to the 400 is. In other words, if I knew that resistance, I could just take the 0.017349, multiply it by the resistance of that little piece of wire, and that would be how much the voltage dropped from the positive terminal of the battery to the left edge of the 400 ohm resistor. We don't have that, so we can't do it. But what I can also do is, now that I know what current's going through the 400 ohm resistor, I can find the voltage across it. So the voltage across the 400 ohm resistor, V400 is what I called it, is actually equal to 0.017349 amps. And that all times 400 ohms. So I'll say times 400, and that gives me 6.939 volts. So what that means is the left-hand side of the 400 ohm resistor, like the bubble shows, is essentially at 12 volts. But now if you want to know what the right-hand side of the 400 ohm resistor is, well, that bubble can come from taking 12 and subtracting from it this number, the 6.939. So for this gate, I get 5.061. So that's what the voltage is at that point. And of course, that's also what the voltage is at this point. And that's also what the voltage is at this point. So I think you can see now, since I've done that, we can now tell exactly how much voltage is across the 500 ohm resistor and how much voltage is across the 700 ohm resistor. So that allows us a quick way to figure out the current through the 500 ohm resistor and the current through the 700 ohm resistor. Not only that, we already know what the voltage across the 500 ohm resistor is. So I can say V, oh, I should do this in red, sorry. I can say V500 is equal to V700, both of which equals 5.061 with one extra sig fig. And now we know the voltages across those resistors. Everybody see how I did that? Does it make sense? Go ahead.
Is that just 12 minus the other one?
Exactly. Yeah, just 12 minus the 6.939, because that's how much, according to Ohm's law, that's how much the voltage has to drop in being a current going through a 400 ohm resistor. Does that make sense to everyone? Anybody have any questions? All right. Well, now I can figure out that the I500 is in fact just going to be the voltage, which is 5.061 over 500 ohms. I'll leave off the units. And that gives me, I'm going to take the 5.061 and divide it by 500. And that's going to give me 0.101. Excuse me, I did too large a magnitude on that one. 0.0101 and then a 2 amps. And I700 is done the same way. It's 5.061 over 700. Divided by 700. And I got 0.00729 amps. So now I've actually figured out all the information about the circuit. And it's just by making sense of how voltage drops given Ohm's law and that sort of stuff, but how voltage drops when you know the current and resistance on the actual object. Remember, we read it as current going through an object and voltage across an object. So I've now managed to figure out what the voltage is across each of the elements. For instance, the 400 ohm resistor has a 6.94 volts across it. The 500 ohm resistor and 700 ohm resistor both have 5.061 volts across it. And I know all the currents. In fact, it'd probably be easier if you move the decimal 3 places to the right, in which case you'd see we've got 17.3 milliamps coming from the battery and also going through 400. And we've got 10.1 amps going through the 500 ohm resistor, and we've got 7.229 going through the 700 ohm resistor. Now, Kirchhoff's junction rule says that since that current for 400, the IB versus the I400, since that current breaks off into two legs, the current through the 500 and the current through the 700 are supposed to add to give you the total current from the battery, and therefore the total current for the 400. So if I actually add those, I should get that 0.017. So I'm going to do that now. if I take and add 0.0072294, I'm adding to that 0.01012, and I got 0.01735. So plenty close within the sig figs. It gave me 0.17349. So it really is as pretty much tight on the money as you could possibly guess. Okay. So write that down somewhere that you checked. Or actually, I'll do it this way. I'll write it on here so remember. So each time you do something where you worked out voltages like that, you want to make sure that all those voltages add up to the same voltage as anything that's in parallel with it, which in this case, you could be talking about the battery, meaning if I added the voltage of the 400 ohm resistor and the voltage of the 500/700 ohm resistors, those should add up to give me 12. So I can check that as well. So I will write this somewhere else. I'll say check V400 plus V500 equals 12.0 volts. And I see that that is in fact the case. So these little areas you should really highlight just to remind you. So for instance, I'm going to highlight this and highlight this. Okay. Any questions on that? I fit it into a pretty small area, I know. All right, we'll move on. We've got a more complicated circuit coming now. This circuit is quite a bit more complicated. What I'm going to do is I'm going to start off with, for starters, not using a highlighter, but I'm going to start off with a 9-volt battery this time. And I'll put it right here. And then I'm going to have my 9-volt battery go out. A wire coming out from the positive end is going to go all the way up to here. Okay. I'm trying to make use of the niceness of my program to make lines straight and stuff. So sometimes it's kind of a little more convenient, looks better. All right. Now, about halfway through there, I've got another line that comes off and goes to the left. And in this case, it is a 40 ohm resistor. And then I go a little further over still, and I got a 1 ohm internal resistor. Then I got yet another battery, and it'll go right here. I'm going to come down here and use this battery as a 20 ohm resistor. Excuse me, this part of the leg anyways. And I'm going to put an internal resistance in this battery as well. And in this case, it's going to be 1 ohm as well. Now I've got one more part, and that is a wire up here has a .30 ohm resistor right there. This battery, by the way, at the bottom is 80 volts. Excuse me. No, this battery is 9 volts. And actually, I got a bunch of stuff jacked up. I just realized I copied from 2 different problems. Ah, poop. Okay. I'll save that one for next. Everything looks okay on that except for the 9 volts, which was supposed to be, of course, 40 volts. So we'll skip this one right now. Actually, what I can do is this. Cut. And I should be able to paste now. If I can just find how to paste, that'd be really cool. Paste, paste, paste. Whoa, don't know what I did there. Copy the page, copy the page, copy the page. Do not see paste. Why are you aggravating me so? Oh well. What I will do is go back to here and just redraw a new circuit and be done with it. All right, sorry about that. So what I have again, this time I'll try to keep my eye on the proper figure. I'm going to have a current carrying wire coming from the 9-volt battery. It's going to break off and go to a resistor that has a resistance of 6.0 ohms. Then that wire is going to break off into 2 parallel legs like such. And this top one's going to be an 8 ohm resistor. And this bottom one is going to be a 4 ohm resistor. And here's where I jacked up last time. Okay, this one's going to be a 5.0 ohm resistor. And then I've got one more, and now you can see why they get a little confusing, why it's so easy to accidentally look at the wrong circuit while you're in the middle of the other circuit. And that resistor up there is 10.0 ohms. The battery is 9.0 volts. What I want is all currents and voltages equals question mark. So the first thing I got to do is label, pretend I know what currents are acting, and assume I know what direction they're going, and draw them accordingly, and then follow the rules. Once we get to Kirchhoff's rules, then that'll be a lot easier. But right now, I'm going to say there's probably a current going this way, and I'm going to call that just plain I. Then there's a current going this way. I will call that I6. I think y'all can see why. I will assume, just for the heck of it, because I kind of think it might go the other way, I'm not really sure, but I'm going to assume this is going this way, and that's I10. And then I have an I8 here and an I4 right here. Notice the I5 is the same thing as just the plain I. Let me zoom in so y'all can see this. Well, okay. In fact, let me zoom in a little bit bigger and make this a little bit more reasonable. This one's what I call I4. And for some reason, all of a sudden, the lines are drawing really fat. Well, I know part of it's because I zoomed in, but I guess all of it's because I zoomed in. Okay, so now I think everybody can see what I'm talking about on these currents. I've basically labeled them according to the resistor's value that the currents go through. The main rule is that each wire by itself has a current going through it. So for instance, from this dot to this dot is two wires, one that goes through the 8 and one that goes through the 4. Therefore, I have 2 separate currents there. And then, of course, you see that I6 feeds those 2. And you see that those 2 come back together right here. And therefore, the I6 also exists in that little piece of wire that I'm labeling sort of red. Everybody see that? So that's I6 as well, even though it doesn't necessarily look like it. Okay. So I'm going to first off eliminate the parallel resistors 8 and 4 ohms, because 1/8 plus 1/4 is equal to 1 plus 2/8, which is 3/8, which means the R equivalent for this one is 8/3, which is 2.667 ohms. So now I know I can replace this setup with basically a 6.0 ohm resistor running in series with a 2.667 ohm resistor. That is all in parallel with a 10.0 ohm resistor. And you can say that this in fact goes off straight down here and runs into our 5.0 ohm resistor. And that's it. Okay, so now we've gotten another version of the circuit. Of course, the 6 and the 2 are in series, so that means another R equivalent, which I'll call R equivalent 2, is equal to 6.0 plus 2.667 ohms. And of course, that gives me 8.667. And you see now that, in fact, I've actually certainly am using 2 extra sig figs on there. So this circuit is now equivalent to basically a circuit that has a 8.667 ohm resistor in parallel with a 10.0 ohm resistor, and then a battery, and of course a 5.0 ohm resistor. Now I've got a 10 and a 8.667. This is a little harder to do. I can't just do it with my head. I'm gonna have to say 1/R equivalent 3. These are parallel. The 10 and the 8.667 are parallel. So I'm gonna say 1/10.0 plus 1/8.667. Now you could actually realize that that's 8 2/3, so you get 24, 25, 26. You could call this basically 26/3. Well, 3/26 would be more correct. Okay, so I could do that. I could get a common denominator. I could just, multiply the 10 by 2.6, for instance, and do that in top and bottom. Then I have a 26 denominator, and that'd be 2.6 plus 3 would be 5.6. So that would give it to you, but we don't have to be brilliant. I'm just going to say R equivalent 3. You guys should try to work this out on your own as well. I can do in my calculator, I'll do parentheses 1 divided by 10. And then I do plus parentheses 1 divided by 8.667. All of that gives me 0.21538. And now I can flip that over by raising it to the -1 power. And that gives me 4.643 ohms. Okay. 5 point, by the way, just to let you know, 5.6 divided by 26. That gave me the 0.2153, just like I had before. And then when I, of course, flip that over, I would have gotten the 4.643 again, just like I thought. So that way would have really worked. It's just a matter of I figured it was not going to make it any easier for you to see me doing quote unquote magic arithmetic. Now we have a 10 and 8.667. They are clearly in parallel with each other. And we've now reduced them to a single resistor, and that single resistor has a value of 4.643. And notice I'm using these equals to just suggest that the circuits are equivalent. That's going to be in series with a 5.0 ohm resistor, and that's all going to be powered by a 9-volt battery. Okay, so I think you can see finally, talking about the current I, which is what we chose to call it, we can see that 9.0 volts, this is V equals IR, 9.0 volts is equal to I times, I'm not taking the time to draw another circuit. I think y'all can guess that the equivalent resistance is 9.643. Easy for me to say, right? And yes, it looks like I wrote that in blue, so yay for that. That's just gonna have to stay. That means that I coming out of the battery, which also happens to be the 5 ohm as well. I get that by dividing 9 by 9.643. 9 divided by 9 point, and I did copy that right. It's 9.643, right? Yeah. And that gives me 0.9333 amps. So I equals I5 equals 0.9333 amps.
Why does it equal I5?
Okay, what you got to realize is whatever leaves the battery has to come back in the battery as well. And there's only one path. See, when you get to, for instance, this junction right here, the 0.993 is going to, or you can call it right here since that's the original circuit. The 0.933 is going to split up into an IP and an IB, and then, or excuse me, an I6. And then the I6 is going to split up into I8 and I4, and then the I8 and I4 come back together, and that makes the equivalent of I6 again. But also IP will be leaving that junction. So in order for that junction, this junction over here to be right, then this must be I as well. Does that make any sense?
Yeah. And why is I10 going down?
I wanted to show you that it doesn't matter if we accidentally choose what we think is the wrong direction. What we're probably going to find is, in fact, that this side of the battery, or excuse me, this side of the resistor is a high voltage and this side is low. But one of the problems is when you're solving these problems, you actually have to put down a direction for each of the currents. And if you're hamstrung by worrying about getting the wrong direction, then that's going to kill you. You shouldn't be wasting any time on that, because if you get the wrong direction, all that's going to happen is when you solve the system of equations, you'll get a negative current. So I'm just trying to show you that that doesn't really matter. It's all going to work out once you guess them, and then you can figure out stuff in there. So in other words, I'm probably going to get like I10 being a negative number or some other weird stuff like that. That was Sydney. All right, so now that I've gotten I5 and I can realize that that I5 is actually going not into a true 4.634 ohm resistor. It's actually going to break apart, and part of it's going to go into a 6 ohm resistor. So not only that, what we know is this right here, according to our bubble technique, is 0 volts, which means this is also 0 volts. And we can now actually figure out what this voltage is going to be as follows. I did make that I4 awful small. Let me see if I can get it better now. No, that red did not help the situation at all. There you go. Okay. So what we know is that since the I went through I5, if we take that I and multiply it by 5, then we should get the voltage drop across it. So 0.933 times 5 gives me 4.667. 4.6666 in other words. So V5 is equal to I5 times 5.0 ohms, which equals 4.6666, carrying a couple extra sig figs there. That's the voltage. And what that means is this bubble right here should be 4.67 volts, basically. So now we know the voltage there. That also happens to be, if you pay close enough attention, that's got to be this voltage too. I want to draw it in blue, so I redrew it. That's got to be that voltage and that voltage as well as this voltage. Does that make sense? All those dots I just drew, the one next to the 4, the one next to the 8, and the one next to the 10, as well as the one or the arrow at the top of the 5, all of those points have the same voltage, which is 4.67 or 667, however you want to say it, volts. Because of that, we now know a lot of stuff. So for instance, our bubble right here is 9.0 volts. That means our bubble right here is also 9.0 volts. And our bubble right here is 9.0 volts. Because again, when you go across the wire, you're not changing elevation. Remember, we're supposed to think, well, you didn't have me for lab, but I did try to explain it in class one time. What you think of is each battery is like a set of stairs or a water pump or something like that. So that when you go in that little wire from the 5 ohm resistor all the way up to the short side or the negative side of the 9-volt battery, that's all the same elevation. We'll call that ground level because it's going to be what we call 0 volts, as I already showed you with the bubble. And then I'll take the stairs from the short terminal of the battery, which is the negative terminal. I'll take the stairs up to the long terminal, which is the positive terminal. And now I'm up at a height of 9 volts. But I will stay at that height of 9 volts until I get to the left-hand edge of the 6 ohm resistor and until I get to the edge of the 10 ohm resistor, again, the left edge of both of those. Does that make sense? So try to think of circuits that way. It will actually help you. I've now gotten a couple different things. In fact, I now know that the voltage across the 10 ohm resistor, V10, is actually equal to 9.0 volts minus 4.6667 or whatever volts. So if I do 9 minus that, I get 4.33. Like, duh. Okay. So I now know the voltage through the 10 volt, through the 10 ohm resistor, across the 10 ohm resistor, excuse me, since I'm talking about voltage. I now know that voltage across it is in fact 4.33. And of course, Ohm's law tells us that 4.333 volts is equal to I10 times 10.0 ohms. And that gives us I10 is equal to obviously 0.4333 amps. I don't like how small I wrote that. Does everybody understand how I did what I did right there?
Yeah.
Okay, so now I've got a lot of stuff figured out. I've got V10, I got V5, I got I, which is also I5. I got I10. So now it's just a matter of going through the rest of the stuff. Now, what we know is that I breaks up in, or that I plus I10 both run into each other according to what I have drawn. And that should give me such a voltage that when I go across the 6 ohm resistor, or such a current that when I go across the 6 ohm resistor, I have exactly the right voltage such that that voltage added to the 8 volts, or excuse me, through to the V8 gives me the right answer. I don't know that yet, but drawing that IP as 10 here could say that that 10 amp, or that 0.433 amp current that could be coming down and entering the junction, or it could be going up and entering the junction. What I do know though is that the 9 ohm, or excuse me, the 9 volts is at the left side, and the 10 ohms is at the or excuse me, the 4.67 ohms is at the right side. So that tells me my current was actually in the opposite direction. So I'm going to now say in opposite direction. So this is wrong. Okay, so that's all that happened with this one. When we do Kirchhoff's laws, you'll literally have a chance to solve for it, and it'll give you a negative. In this case, you had to look at it and say, oh, well, I see I went from a higher voltage to a lower voltage by going through the resistor from left to right. And we know that resistors are always decreases in voltage as long as you're going the direction of the current. So I10 should technically be called like a negative there. I could put it up here if I wanted to. I would do it in blue just to show. I just want you to know I did not calculate that. I had to determine that. So, all right, now that we have that, we can also say, well, I know that basically 0.933 is going into the junction. 0.433 of, or excuse me, 0.4333 of that is going up to the 10. So I6 has got to be, make sure I'm in red, I6 has got to be equal to, or let me write it as Kirchhoff's junction rule. Remember, Kirchhoff's junction rule says the sum of the things coming in is equal to the sum of the things going out. So Kirchhoff's junction rule gives me, after I've made that discovery that IP is that I10 is the wrong direction, it's allowed me to make the discovery that I is equal to I6 plus I10, so that I6 is just equal to 0.9333 minus 0.4333 amps. So I6 is going to be 4.66. So I've now got another answer for I6. And in fact, that allows me now to determine what the voltage is at the right edge of 6. We know that V6, we know that, dang it, eraser in you. We
Is
know
it
that
0.466?
it's 4 point, yes. No, this, sorry. Yeah, that should have been 0.433. Ooh, let me make sure I even did the right. Oh, that's what happened. Thanks for catching me on that. I copied that identical number, but it was the voltage, not the resistance. So this should have been That number was actually right. I don't know why I erased that. So 0.9333 minus, 0.4333. That should give me, in fact, 0.5. So nice catch. Thanks for catching me on that. I might not have gotten it till the very end, and then I'd be beating myself against the wall and in the head to try to figure out what went wrong. So there's my 0.5 amps is what I6 is. And again, according to Ohm's law, V6 is going to be equal to, it's going to be equal to 0.500 times basically the ohms, which is 6.0 ohms. And that's going to give me 3.00 volts is equal to V6. That means since the other edge was 9, it's going to drop from 9 down to 6. So now my bubble says 6 volts, and the bubble points to this mark and this mark and this mark too. So now what we know, since I know the right-hand side of the 8 ohm resistor is 4.67 and the left-hand side is 6, then I know that the voltage across the 8, V8, is in fact going to be equal to 6.0, or excuse me, did I mean to say 6? Yes, because it's -3. So 6.0 volts minus 4.667 volts is equal to 1.33 volts is all that's across the 8 ohm resistor. Now, because they're in parallel, V4 is also supposed to equal V8. So V4, dang it, why do I keep doing that? So V4 is also equal to 1.33 volts, which you can also see if you wanted. I mean, if you want to verify it, you know that the voltage across it is 6 minus the 4.667. So we've still got basically 1.33 volts is equal to, well, I'm just repeating what I'd already said. So I'll just leave that alone. I think y'all should follow that where it is. Anyways, any questions on that part yet? Okay, so now what we figured out is the voltage of the 8 ohm and the 4 ohm part, and we do have a check, by the way. V equals IR means that we should be able to find I8 and I4. Since 8 is twice of 4, we really expect the current through the 4 ohm resistor to be twice as big as the current through the 8 ohm resistor. And to be honest with you, we only had half an ohm going in. So you're basically going to take 2/3 of that should be the current in the 4 ohm resistor. So if I multiply 0.5 times 0.66666, whoa. I get 0.33333. So I expect the 4 ohm resistor is going to have 0.333 ohms, and then the 8 ohm resistor is going to have 0.1665. But Ohm's law should get us that too. So I'm going to say I8. I'm going to say I8 is supposed to be 1.333 volts divided by 8.0 ohms. And that gives me exactly what I hinted at, which was 0.1667 amps. Well, again, way more sig figs than is reasonable. And then finally, I4, which we suspected would be twice as big, is equal to it's equal to 1.333 volts divided by 4.0 ohms. And that gives me 0.333, which is exactly what I said. Stupid thing keeps erasing. 0.3333 amps is the current through I4. I mean, through the 4-ohm resistor. Okay, so that's a way you can actually work out all the details of one of these problems. But as you can tell, that's sort of just winging it. I'm pretty much looking at it saying, okay, well, I think I'll try this. Okay, well, I'll try this now. You can go back and check now. For instance, you should check. I'll write it again. You should check that the I6 is equal to I4 plus I8. That's one check you should do. Another check you should do is, well, we already set that one up. Actually, everything else has been checked because we used a lot of the voltages and stuff like that to work out. So yeah, everything's good. The only thing I would double check on is that I6 is in fact I4 plus I8. I can see that I4 is 2/3, and actually I8, I think that's 5/6. No, maybe not 5/6. Oh well. Anyways, if I add 0.1667 plus 0.333, I do get a roughly 0.5. So now I've even checked it. And now I'll put my highlighter on and say, good for me, Mr. Younger. I did that. Okay. Don't forget that that's a check, not a voltage. Any questions on that one? Okay, we've still got about 17 minutes left. That's good because I have at least one more I want to do for you guys. And it's this one right here. So this is a little more complex. It was the one I've already drawn for you, but never mind that. Just the nature of the beast, I guess. So I'm gonna do that. I'm gonna do that. Whoa, what the heck is happening here? It's like it's not taking my drawings. Okay. I'm gonna go over to here. Go over to here. Now with this one, I'm actually going to have, oops, I drew my battery backwards. There's my battery. And I even left off a spot. I forgot to leave off a spot for the internal resistance. So I'm going to go from here to here, and that's going to be 1 ohm resistor. And then I'm going to run the line all the way up to here. So it'll be nice and straight. And then all the way up to there. So it'll be nice and straight. The top part over here is going to have a resistor like that. And that is a 30 ohm resistor. That's a 30 ohm resistor. Now in the middle of this, I'm going to have, for starters, a 40 ohm resistor. And then followed by that is a 1 ohm resistor. And then I have a battery this way. And that goes to here. Another thing I left off was right here, I need another resistor. And you see how much it's similar to the other one. So you can see why I made such a pain in the butt mistake in putting this all together. So there's the last resistance, and that in fact is 20 ohms as well. My voltages are 45. Actually, let me double check my figures here. Make sure they are what I'm saying they are. I think they're 45 and 80. Not that one, not that one. Oh yes. Yeah, 45 volts and 80 volts. So this one's 45 volts, and this one is 80 volts. Now, this is one of those cases where we're actually going to use Kirchhoff's rules, and this should give us exactly what we want. What I'm going to do is I am going to make an assumption about the directions. I'm going to say, for starters, this right here, I'm just going to call plane I. And well, actually, I'll call it I1. That'll make a little bit more sense. And then I'm going to say that this current right here is I2. And I'm going to say that this current right here is I3. You'd think I'd find a better place to write that I2. Let me draw it here. And then say this is I2. And then that way I can get rid of this mess. Okay. Now, Kirchhoff's rules say that basically his loop rule says if you go in a complete circle, then all of this voltage increases and drops will add up to give you 0. So what I'm going to do first is I am going to go around the entire outside loop. And then I'm going to go around the bottom loop. So when I go around the outside, I am going to start right, let's say right here, and go to the right. So the first thing I get, here's my solution. The first thing I get is plus 80, because that's how much the voltage increased in going from the short leg to the long leg. So it's plus 80. And then notice I'm going to go minus 1 ohm times I1 minus 20 ohms times I1. So instead, I'm going to say minus 21 I1. Everybody see why I did that? The 21 I1? The 1 and 20 are in series, so they just add. Next, I'm going to get up to the top right corner and go through the 30. Notice I'm going the opposite direction of what I chose the current to be. So that is, in fact, a voltage increase. And that voltage increase is 30 I3. And I'll write this here. Okay. Now I can come back. I don't run into any more elements before I get back to that blue dot. So I can just say this is all equal to 0, and I'll call that equation 1. And that came from the outside loop. Okay. Now I'm going to do the bottom loop. The bottom loop starts with plus 80 again. So I'm going to say plus 80. And then it also starts with minus 21 I1 again. And then it goes plus 45, because obviously I've got to stay in the bottom loop. That means I have to hang a left at that junction. Notice by going to the left through that node, through that string of wire, I'm actually going the direction of the current. So I now do minus 41, 40 for the resistor and then 1 for the internal resistance. times I2. Now there's nothing left between me and the blue dot I started at, so I can say equals 0, and this is going to be called equation 2. Finally, I'm going to apply Kirchhoff's junction rule. So this was the lower loop right here. Now Kirchhoff's junction rule is going to give me that I2 plus I3, excuse me, I1 plus I3 are actually entering that junction, and only I2 is coming out. So I'll say that's equal to I2. I don't know why I keep writing 3 here. And that's equation 3. So we're running a little short on time. We only have like 9 minutes left. So I want to make sure I get through this part. And I'm going to draw on here a problem that you can work out. It's actually a problem in your book where they're jump starting a car battery. Your author made a mistake in the drawing, but worked it out with the number as if he didn't make the mistake. So I'm going to get you to completely do that circuit, get my answers or prove my answers wrong or whatever, and that's going to be extra credit. So you'll see that drawn on the bottom of these notes. I'll probably do it on camera still too, so that can help you. But now the next process I'm going to go through in solving this system is I'm first going to take equation 3, and I'm going to solve that for I3. So this implies, I'll call that new equation 3 prime, but that implies that I3 is equal to I2 minus I1. Okay. Now I'm using a technique here. I don't know, what technique to use, but I know that I'm trying to eliminate 3 variables, and I have 3 equations, which is exactly what I need. If I have too many, it can be actual bad and unsolvable. If I have 3, it's still not guaranteed a solution, but at least you have a chance. So now I'm going to take that version of 3, we call it 3 prime, and I'm going to plug it into 1. So 3 prime into 1 is going to give me this. I'll say 80 plus, or excuse me, 80 minus 21 I1. And actually, I shouldn't do that. Let's do this. Let's go ahead and combine our 80 and our 45 and call that 125. See that the 80 and the 45 are just pure numbers, so I can go ahead and jump with that. So I want to say 125 minus 21 I1 minus, oops, I'm plugging in the wrong equation. No wonder. That's okay. I'll do that later. Well, you'll remember that I actually accidentally plugged it into 2 instead of 1. So now I have 80 by itself. That makes a lot more sense. I was like, I don't remember being there being 1 there. I got 80 by itself minus 21 times I1, and then plus 30 times I3, which is I2 minus I1, and that all gives me 0. And now I can distribute the terms and get 80 minus 21 I1 minus or plus 30 I2, and then minus 30 I1, which I can now get like terms because I've got 21 minus 30, which is negative 51. So I'm going to say 80 minus 51 I1 minus or plus 30 I2 is equal to 0. And I think the smartest thing I can do with that is go ahead and solve it for I1. So if I solve that for I1, you can see I1 is going to become, when I put it on the other side, it'll be positive 51 I1, and I'll have 80 plus 30 I2 in the numerator, And then I just have to divide by 51. And I'm going to call this equation 4. Okay. Now I'm going to plug 4 into equation 2. So when I plug 4 into equation 2, now I can combine the 80 and the 45 to get 125. And then I have minus 21 I1. So instead, I'm going to say minus 21 times, and don't forget fraction bars are parentheses. So you've got to distribute here. I'm not liking how that 2 came out, and I'm afraid it's going to make it where someone can't read it. Okay, so 80 plus 30 I2 over 51, that is completely I1. Now I've got minus 41 I2, and then I've got all that equals 0. Now I can actually distribute the 21 over 51 times the 80 and all that stuff. When I do that, I end up getting 125 minus, I'll take 21 divided by 51. And then I'll multiply that by 80. And that gives me 32.94. And notice that's just a pure number. So that came, just in case anybody wonders, it comes from this, and this. That's what gave me that. The next part is negative 21 times positive 30. So negative 21 times 30. And then I'm going to divide that by 51. And of course, that's going to give me a negative, that's going to give me a negative 12.35 I2 minus 41 I2 is equal to 0. So I can add 12.35 and 41 and get 53.35, and I'll put them on the other side. So now I've got I'll switch it to the left side. So now I've got 53.35, and that times I2 is equal to, now I'm going to take since I've already use those two things, I'm now going to take the 125 and subtract 32 from it. 125 minus 32.94, and that gives me 92.06. Okay, and then finally, I2 is going to be 92.06 divided by 53.35. That's supposed to be a dot there. And that gives me 1.726. And I happen to know that's exactly the answer I got the last time I worked it as well. So we now have current I2. I have an equation for I1 in terms of I2. So I'm going to go ahead and use that to find I1. Or I could have plugged it in equation 1. Nope, I could plug it in equation 2 and solve for I1 that way as well. That would be quote unquote the safest, but I know for a fact I got that answer right. So I'm not too worried about it. I just forgot to put the amps on the end. So I'm not too worried about it. I know that I1 is supposed to be 80 plus 30 times 1.726. I'm not even going to write amps up there. I started off without using those units. And then all that's going to be divided by 51. So in this case, I get 30 times 1.72. And then I'm going to add to that 80. So I've got 30 times 1.726. and I'm adding 80 to that. That gave me 131.77. Over 51. And this gives me 2.584. I do remember this is also being the right answer. So that's I1. And I'll box it off in my blue box, as I always do. And now I can use equation 3 if I want to go ahead and figure out what I3 is. Specifically, I want to use 3 prime. So 3 prime tells me that I3 is equal to I2 minus I1. And I2, of course, is 2.583, or excuse me, 1.72. Now I'm going to subtract from that 2.584. And that's going to give me negative 0.8581 amps is equal to I3. And yes, that's right too. When I was looking in your book, not earlier when I read the chapter, but just when I was perusing it, I don't recall seeing this problem anymore. This used to be a problem that was in the text. It might still be, I might just have missed it when I was just going through it. But either way, this is ultimately how you can solve these. You can use Kramer's rule. You can use Gauss-Jordan method. The main thing is this is another capstone skill that you guys have to have in this class. Like I've got a few skills that anybody that makes it through to that's going to pass 241, they need to be able to, for instance, add vectors, take a cross product, solve Newton's laws of motion, solve Newton's laws of gravity, and solve basically mass on a spring and pendulum problems. In this course, one of the things includes combining a system of 3 equations, 3 unknowns, or even 4 equations, 4 unknowns, and be able to solve that by hand. Okay, so you should be able to do this at least once or twice or 3 times by hand, and then from there on out you can make matrices out of it and let your calculator do it or whatever. But there is a chance that on your midterm or on your final or on some future test that I'm going to ask you to work out details of solving such a system. Now it's 6:43, so time's definitely up. You guys are free to go. I am going to draw this other part onto this thing, and I'll sort of explain what's going on with it on the video, so y'all can just dial up the video, which I'll put on in this week's module. Even though I don't usually do that, I'm definitely going to do it this time. So it should be up sometime tonight or first thing tomorrow. Have a good one, everybody. And Michael, you have a question for me?
Yeah, I have a question about the midterm.
Yes.
Is that test going to be curved, or is it a static grade?
It's pretty much a static grade. But I definitely work hard to make sure you can fix it on the final. In other words, when I see there's a problem where, for instance, a student might not get do too well in the midterm, I usually work with them a lot to make sure they don't screw up on the final, and then their grade normally pans out quite good. But yeah, it's a one shot. You need to study for it well. And the best way to study is by taking these tests, these practice tests that I've been giving you, and do them as many times as possible without looking up stuff. If you can consistently do a one of the practice tests consistently without looking up, maybe get 2 or 3 in a row at an 80 or higher without looking up anything, then you're probably in a good spot. If you have to look up more than one question every 2 tests, I'd say you're not quite ready.
Okay.
Okay. And if we're behind, we don't cover as many chapters as I thought we were planning on, then I'll just truncate what number of chapters or which chapters are covered on the midterm. So sometimes, normally my midterm includes equation chapters 26 and 27. This one might stop on just 27, or excuse me, 26. Or I might, depending on when it is, I'm not remembering exactly right now when the midterm is, but depending on what it is, I will have normally the last two tests, chapters that you tested on, those will be the last two tests on the final. So if we only get through chapter 28 by the time the midterm comes and you haven't been tested on 27 and 28, then the test is only going to be up through 26. Hopefully that explains it. Anybody else have any questions? Okay, I'm going to start writing down this problem as it's shown in your book. And I'm going to sort of explain what's going on. So for starters, what you have, and that's no pun intended there, but for starters, what we're going to have is just a weak battery in line with a line with the starter motor. So I'm going to put a starter motor down at the bottom here. So this is basically like the starter of your car. We'll treat all electronic devices like this, or electrical devices like this, as if they're just a resistor. So I'm just going to draw a resistor in there, and I'm going to say R is equal to, I think that one was, let me check, hold on. I'm looking because I copied it and took a photograph of it. So knowing how I'd have it that way, but obviously it's not always that easy to look at. And one of my students showed me how to use the to actually take a whatever that wide photograph is. The word is escaping me right now. But anyways, that's not been the greatest thing for me because it doesn't necessarily make that clear of a picture. So the resistance of the starter engine is 0.15 ohms. So it's not unreasonable for a electric motor, like a washing machine motor or something like that, to act as if it's a very low resistance, like 1 or 2 ohms or even smaller. In this case, we're going to run from there a wire out to here, and then another wire out to here. And thank goodness I put that on the straight autocorrect, because it really would look bad otherwise. All right. Now, in addition to that, that goes up and runs to the actual battery for the car. And the battery for the car, this is the part that the author seems to have made a mistake in with the figure. Specifically, he says the starter has a resistance of 0.010. It then goes into what he's calling a weak battery. And the weak battery actually has a voltage of, if I remember correctly, 10.1. Yeah, 10.1 volts. Okay, so this is 10.1, dang it, stop it. 10.1 volt weak battery. So first off, we want to know what I weak battery is. In other words, just that part of the circuit. But then we're going to put all this other part of the circuit in there, and I'm going to want you to solve it like you just learned But in this case, you're going to solve it using the actual resistance value they gave you, which was the 0.01. Okay. I'm even going to take it one step further and give you the actual resistances of the jumper cables, which the book did not do. It actually used that as a separate problem part and said, hey, how many ohms is the jumper cable wires? So that was kind of weird. But anyways, the way I'll do that is I'm going to put my jumper cable resistance right here. Whoa. And that is 0. And you're gonna be surprised, but this is a pretty realistic representation of the resistance of a jumper cable, 0.0025 7 ohms and 0.0025 7 ohms are the jumper cable resistances. And now from there, I'm going to go up to here and to here. And what I'm going to put is a battery that's actually in good shape. But oddly enough, despite being in good shape, it seems to have a higher internal resistance than the bad battery. That's the mistake I think he made. And I don't think he realized he made it because it was made in the figure drawn by some artist that, you know, he didn't draw. That one has a voltage of 12.5 volts. So your job is to work this out. What I got was weak battery current was 63.13 amps. And then what I got for I1, which I'll label it like this, this is I2. This is I3. And this is, excuse me, that one's I1. That would have been bad. That one's I1, and then this one is I2, and then this one right here is I3. So when I did that, I got that the currents were I1 equals 87.81 amps. I got I2 was equal to negative 19.21 amps, and I got I3 was equal to 68.61 amps. So for extra credit, solve, let's see, I don't want to say it that way. Solve the bottom circuit for I weak battery. I mean, without the jumper cables connecting the good battery to the circuit. So solve the circuit for I3, then solve the complete circuit showing your manually solving the system of equations.
What does the WB stand for?
Weak battery,
Is that without battery?
weak battery. So only
Okay.
when you're using the weak battery, in other words, that whole jumper cable, both of those jumper cables are gone, and the 12.5 volt battery is gone as well. Okay, I'll put a place on the module for this, but that's basically the extra credit problem. It counts, like I've told you before, basically I substitute that grade for your lowest homework grade, and that's how my extra credits work. So anybody have any questions? I see that only 2 of you guys stayed, but I appreciate you staying, even though you obviously weren't required to. Hopefully you didn't miss anything. Y'all don't have lab tonight, do you? That's right, you don't. I think y'all meet.
No,
Yeah, okay.
we don't have lab.
All right. If you have any other questions, you can ask me, or you're free to go and you go ahead and split, whatever you want to do.
Sorry.
Can I stop sharing the screen, or do y'all need something off of it still?
No, you're good.
All right, take care.
All right. Thanks, Michael. Thank you, Christina.
Thank you. I found that equation in the book.
Yeah, it was funny you mentioned that, because I just happened to click on my book and it popped up as equation 2516. I was like, dang it. So I don't even know where it came from, because I've been there like 4 times. But yeah, so you found it as well, huh?
Yeah.
Yeah, that's crazy. I figured it had to be in here, and I don't even know how I got to the place where I found it, but I just flipped over and there it was. Must have been lucky. But glad you found it, Christina.
Thank you so much.
You're welcome. Let me know if you need anything.
Thank you. Have a good night.
You too. Bye-bye.
Bye.